Good afternoon, everyone. Today we are doing a bit of harmonic oscillation, sound waves, standing waves, and superposition. Okay, so I'm going to start without any ado. And where my name is Lucian Pullen, I'm going to start with oscillations, or rather, I should say, the first section will be on simple harmonic, simple harmonic motion. This is the first section on questions that we will be doing today. Okay, let me just check while I'm getting myself ready, checking everything is fine, it's working, wonderful. Okay, so simple harmonic motion. So in an engine, a piston oscillates with a simple harmonic motion so that its position varies according to the expression. Now they didn't give the expression there, but I'm going to give it. The expression is x, the position x is equal to 5 cosine, open bracket, 2t plus pi over 6. This is the expression that they should have given there, but I'm giving it to you now. Okay, where x is in centimeters and t is in seconds. It, they ask us it. Let me just scroll here so you can see it. At time t naught, find the position of the particle. So at time t naught, find the position of the particle. Okay, so number one, at time t naught, find the position of the particle at t naught. So all you do is you just plug in x is equal to 5 cosine 2. You plug in where it's t, you plug in naught, pi over 6 plus pi over 6, and then you will find where it is at x equal to naught. So this is 5 cosine pi over 6, and that 5 cosine pi over 6 is approximately 4.33 centimeters. Okay, just problem. Hey, I'm in a class now. No, 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 you can arm it. Yes, thanks, thanks. Okay, my apologies. Someone just wanted to arm the building there quickly. So you plug in 0 there, and you get the position at time 0, which is 4.33 centimeters. Remember, it told us it is in centimeters. Question number 2, they ask us find its velocity. Okay, the velocity. This is the formula. X is equal to 5 cosine 2t plus pi over 6. Then they ask us to find its number 2, the velocity. How do we find the velocity from position? Okay, velocity is equal to dx dt, the derivative of the position function with respect to time, d dt of the function 5 cosine 2t plus pi over 6. Therefore, if we differentiate, 5 is a constant. The derivative of cosine is negative sine. We'll just write the negative up front. That's sine 2t plus pi over 6. And then we find, this is we're using the chain rule, We find the derivative of everything inside with respect to t, which is just 2. So what we're left with at the end is 2 times negative 5 is negative 10 sine 2t plus pi over 6. This is just a chain rule. And they ask us at time naught find the position and at time naught find its velocity. So we plug in 0 there. We will find its velocity at time naught. So negative 10, by the way, this is centimeters per second. Negative 10 sine, so it's at time naught. V, where time is equal to 0, sine of 2 times 0 plus pi over 6. The answer is, so the velocity when time is naught is equal to 5 centimeters per second. 5 centimeters per second. And you can check that the sine of pi over 6 and multiply that by negative 10. Well, at least that is what I got. I assume the pi of that is a half, which will give that negative 5. And let's check. Yep, that is what they got as well. 4.3, and that's what they got. I forgot that the answer is also here. So, moving on. Number 3. At time naught, find the acceleration. Here they want the acceleration. So all you need to do is to take your formula for velocity, which is negative 10 sine 2t plus pi over 6. That's your velocity. And for the acceleration, you just find the derivative with respect to time of that formula, 2t plus pi over 6. That gives you the derivative of sine is cosine. Okay, that is negative 10. Excuse me, there should be a negative 10 there. Let me rather just write it at the end. Negative 10, you can write it at the front or at the end, it doesn't matter. So it's cosine times 2t plus pi over 6 times the derivative of that, whatever's inside is 2 times negative 10. So in the end, it's negative 20 cosine. See, it's an oscillating function, 2t plus pi over 6. That is the acceleration. Acceleration is dv dt. That's the acceleration. Now we want the acceleration when t is equal to 0. If we plug in negative 20 cosine 2 times 0 plus pi over 6, we have the answer equal to, what I got here is negative 17.3 centimeters per second squared, because we are dealing with acceleration. Let's see if they found it. Negative 17.3 centimeters per second squared. Now we need to find the period. Okay, number 4, the period of that function. Okay, the period of that function. Now we know from harmonic, from wave motion, that period is equal to 2 pi over the angular frequency. Now what is the angular frequency? In this case, let's write out the formula. X is equal to, where's the formula again? 5 cosine 2t plus pi over 6. What is the Angular frequency, it is 2. It's the number in front of the t. So it is 2 pi over 2. The 2's cancel. So the period is just pi seconds or 3.14 seconds. Okay. And then let's see if we can fit in question number 5 at the bottom. What is the amplitude for this motion? The amplitude you can just read off. It's that number right in front. It is 5 centimeters. 5 centimeters. Amplitude is equal to 5 centimeters. And that, ladies and gentlemen, is a question on oscillating bodies or simple harmonic motion. Now let's go to problems for today on sound waves. This is much more interesting. Problems on sound waves, but I didn't find the others interesting. Much more involved problems. So I want to fit something quickly. Yes, that is correct. Done with that. So next problem. Problem number 1 for sound waves now. Okay. A boat. Let me just check. A boat sounds a foghorn on a day when both the sea water and the air temperature is 25 degrees Celsius. So on this day, the air and the water is the exact same, the sea water is the exact same temperature. A boat sounds a foghorn. That is to warn other ships during fog that they are nearby. The speed of sound in seawater is 1,533 meters per second. How much earlier in seconds does a dolphin 1,000 meters away from the source hear the sound than a person in a boat that is also 1,000 meters distant? Ignore the time it takes the sound to reach the water surface. So, sound in this case we have a boat. Okay, we have a boat. The worst boat I can draw. It has a foghorn and it emits a sound. It emits a certain sound. Then we have under the water here. This is terrible water. Under the waves there, 1,000 meters away, we have a dolphin. Now, please don't. Oof. I'm just gonna draw a fish. I can't draw a dolphin. I don't even know why I even tried. So this is the dolphin. Okay, it has a bottlenose. It's a bottlenose dolphin. So there's the dolphin, 1,000 meters away. And then here is another person on a boat. This person is on some barge. Call it a barge. This person is also 1,000 meters away. Now the distance between them is 1,000 meters. The question is, sound travels through the air, okay, to this person here on the boat. Okay? This person hears it eventually, the dolphin hears it while sound travels through the water. The question now is, we know that sound travels quicker in water, it's 1,503 meters per second in water, okay, and in air it's 343 meters per second. They want to know how much, in terms of time, how many seconds before the person does the dolphin hear the foghorn. Okay, let's work it out. Now, what you need to know also or remember is that the time, the velocity of speed, the velocity or speed of sound in air changes with temperature. Okay, so first you need to work out the speed in terms of the temperature in degrees Celsius, by the way. Now, there is something I have written it out in my. There is a formula that calculates the distance, or rather the speed of sound in air as it changes with temperature. Okay, but let me just, I want to go to survey and check quickly, because I have the one from thermal physics. Is it still the same one? Or is it still the same one? Or rather, I have a more modified version, a sharper version, a sharper, more correct. Okay, let's see. Survey and Jewett. Speed of sound in air at different temperatures. Okay, I should know this. I lecture this, but I just want to make sure I have it on my thing here. Okay, I want to show you guys that I'm not sucking this out of my thumb. This is thermodynamics. Superposition, standing waves, Doppler effect, and we still have to get to that. Okay, sound waves travel with, here's the summary. That's waves. I want to see if they actually have it. Does Survey not have it? Because I teach it to my class. Okay, that's the position, that's temperature. Oh yeah, that's transverse. And yeah, there is wave motion. But there is transverse wave motion. Forgive me, I just need to make sure about something. So it should be in sound waves. Yes. I don't show it. I teach it to my class, but Survey doesn't seem to have the formula. Or rather, the summary doesn't have it. This is, oh yeah, here it's speed of sound. There should be one here. Intensity. Okay, let me just check rather, because it seems Survey doesn't have it. Or would it be? No, it won't be on thermodynamics. I teach that section. Let me just check. Yep, here it is. This is the formula I'm looking for. This one has already been, yeah. So the speed of sound changes according to this formula is 3.331, 3 meters per second, which is this actual speed of sound, plus then you add, this is what I wanted earlier on. The speed of sound changes according to this formula. V is equal to 331.3 meters per second, and you multiply it by the square root of the absolute temperature in Kelvin over 273.15. Okay, now this is the speed of sound in air according to certain temperature fluctuations. Okay. Now, if we wanted, let's say, the speed of sound in air at a temperature of 25, like they say here. First of all, let's work out what is 25 plus 273. Then that will be in the absolute temperature. So 25 plus 273, 15, because I already have the answer. So it's 298. So I am doing the full problem, the square root. So that would be, yes, 298, comma 15 divided by 273, comma 15, and you multiply that by that. So your new sound value in air is 346,45 meters per second. So this is your value for air in, your value for sound at a temperature of 25 degrees Celsius. Okay, now I want to check something. The square root function here, square root of fraction function. Okay, oh, brackets, let's use brackets. 298. I'm just actually doing the calculation just to make sure. 15 divided by 273. Excuse me. 273, comma 15. Because I usually just use the I'll show you now. The formula I usually use is 1 comma that, and then you multiply that by 331, comma 3, and you get an answer of 346. So yes, it is correct. The formula I used is just this one. It's the same formula. It's just been simplified. VA is equal to 331, comma 3. I wanted to show you the actual formula. This is what it looks like. This is a simplified version I have, plus 0,606 from thermal physics multiplied by the temperature. That is the same formula. It's just that we get all of the constants out of the way quickly. So we just plug in temperature and then add that. The exact same formula. Okay. Now, and if you were to work it that way out, you would get the exact same value too. So now we have the temperature, the speed of sound in air. Okay. So let's calculate how long it takes for the speed of sound to reach the person first, and then how long it takes to reach a dolphin. So the time it takes to reach the person would be the distance divided by the speed of sound in air. This is the time it takes for the person. Okay, so it will be 1,000 divided by 346, the speed we just worked out, 45 meters per second. That's 1,000 meters. Your answer will be in seconds, and it is actually 2,886 seconds. That is how long it takes to reach the person. But now, how long does it take to reach the dolphin D? So it's the same distance over the speed of sound in the water. I want to see. Okay, there we have the speed of sound in the water. So it will be 1,000 meters. The speed of sound in water is 1,533. They gave us meters per second. If you work that out, the speed is 0.652 seconds. Okay, so it takes 2.8886 seconds to reach the person, but 0.652 seconds to reach the dolphin. Okay, now if we find the difference in time, delta t is equal to the speed, the time it took to reach the person, so TP, minus the time it takes to reach the dolphin, that will be how much faster it reached the dolphin. Okay, so it will be 2, let's do comma, 2,886 seconds minus 0,652 seconds, which gives us, and I did do the answer, find the time, that is 2.234 seconds. 2.234 seconds. Right? So it reaches the dolphin 2.2 seconds before it reaches the person. Quite an interesting problem, and it just emphasizes how that water, the speed of sound in water is different from the speed of sound in air, and how temperature actually has an effect on the speed of sound. Now, that is where we get the 343 meters per second, because we assume it is a temperature of 20 degrees Celsius, which is room temperature. Okay, let me just move to question number 2. And there we have it, 2.24 seconds. We have calculate 2.23, but it's 2.24, whatever. It's a rounding. So, question number 2. As long as you know how to move it, to calculate it. Okay, so a car moving at 36 meters per second passes a stationary police car. So we have a car, it's moving at 36 meters per second. It passes a stationary police car whose siren has a frequency of 500 hertz. In this case, the source is not moving, the observer is moving. What is the change in the frequency heard by an observer in the moving car as it passes the police car? The speed of sound in air is 343 meters per second. Okay. Now, what has been given? The frequency of the source is equal to 500 hertz. The speed of sound, V sound, is equal to 343 meters per second. This is a Doppler effect equation. The change in pitch, the speed of the observer in the car is 36 meters per second, and the speed of the source is equal to 0 meters per second because the source is not moving. Now, what is the Doppler equation for this problem? It says that the change in frequency is equal to the original frequency, or the apparent frequency is equal to the original frequency multiplied by the speed of the source, well, the speed of sound, plus the speed of the observer over the speed of sound. That is the apparent change in frequency. So that's how, because in this case, the observer is moving, the source is stationary. The observer is moving, the source is stationary, the source is 0. So if the source was moving, there would be a plus minus the speed of the source. Okay? So the frequency that is, the actual frequency is 500 hertz. The speed of sound is 343, plus the speed of the observer is 36. The speed of sound is 343. Now you should know, since these two are moving towards each other, the frequency heard by the observer should be higher, and this is what we expect, that the frequency should be higher. So 500 multiplied by 343 plus 36, that's 379. 379 divided by 343. That should be a positive fraction. So fraction should be 1 comma something. In this case, the observer is moving towards, so we use a positive there. The observer is moving towards the source, and that gives us 552, comma, or at least this is what I got, comma 48 hertz. This is the frequency that is heard by the observer inside the car. Okay, this is the frequency heard by the observer inside the car. 552. Okay. Now the next question is, what is the change in frequency heard by an observer as the power passes the? Okay, so this is the as they are moving towards the observer, as they are moving towards the source. Now, what's the frequency as they are moving away? Because we want the change in the frequency that the observer hears. Now, the frequency as they are moving away is the speed of sound. You have the speed of sound again, but this time they are moving away, so it's the observer's moving away. So we have 500 multiplied by, that's 343 minus 36. Same question, just the sign change. 343. In this case, it's going to be less than 500. In actual fact, it's 447,52 hertz. This is the frequency heard as they are moving away. So this is the frequency as they are moving towards. This is the frequency as they are moving away. So the change in those two frequencies. Okay, so the change in the frequency that is heard is the frequency as they are moving towards, and minus the frequency as they are moving away. So the frequency as they are moving towards is 552,48 hertz, minus the frequency as they are moving away from that source is 447,52 hertz. And that gives us a change of 104 hertz, 104,97 hertz. So that is a lot of, that is a big difference in the frequency. So you'll be able to notice it immediately as the car is, as an observer inside the car. Okay, as you're going towards the ambulance and as the ambulance you're going away from the ambulance. It's 104,9, which you can just write as 105 hertz. And let's check. I've already checked. It is correct. Okay, so question 3. Question number 3. Question number 3. A jet plane has a sound level of 150 decibels. What is the intensity? Okay, so how do we calculate intensity? We know that sound level in decibels is equal to 10 times the log with base 10 of the intensity of that sound wave divided by the threshold of hearing. Okay, this formula is in your book. We know that this one is 150 decibels. 150 decibels. That is 10 log base 10 of I. That's the intensity we want. And the threshold of hearing we know is 1 times 10 to the negative 12. So to find that, we divide, it's 15. Let's log 10 of that. 1 times 10 to the negative 12. So if we divide it by 10 on both sides, this is what we get. Now we take the anti-log, that would just be 10 to the 15, the anti-log. So that will just be I over 1 times 10 to the negative 12. So I therefore is equal to 10 to the 15 multiplied by 10 to the negative 12. So I is 10 to the intensity is 10 to the 3. So 1,000 basically. 1,000 watts per square meter. That is the intensity, 1000 watts per square meter, and that is the exact answer that I've shown there. It is simple math. You just plug everything into this formula. In order to answer this question, you need to know this formula, that the decibel is equal, the sound level in decibels is equal to 10 times the logarithm with base 10 of the intensity of that sound divided by the threshold of hearing. Okay, question number 4. Let's check out question number 4. A point source emits sound waves with a power output of 100 watts. What is the sound level in decibel at a distance of 10 meters? Okay, now we have just done this particular problem. Okay, we have just done this particular problem, but or a type of this particular problem. So sound level is equal to B, but so first we need to calculate the intensity of the sound level. Okay, we want the sound level, so we first need to calculate the intensity of the sound. Intensity is equal to the the power, sorry, I'm just thinking P, 4 pi r squared, because it's a sphere, the surface area of a sphere. So the power is 100 watts, if I'm not mistaken, that's 100 watts divided by 4 pi, and the radius, it is 10 meters away. So 10 meters away, so it's 10 squared, 100 cancels, so it's 1 over 4 pi. 1 over 4 pi. That is the intensity in watts per meters squared. That's the intensity. Now they want the sound level, of course, and we know that the sound level B is equal to 10 the log with base 10 of the power, the intensity, which in this case is 1 over 4 pi over 1 times 10 to the negative 12. And if you work all of that out, you should get a sound level of 109. If you do the plug that all in your calculator, I got 109 decibels. 109 decibels, and that is also what the answer should be. Okay, these are simple questions. You just need to remember the formulas. Question number 5. A sculptor strikes a piece of marble with a hammer. Okay, find the speed of sound through the marble in kilometers per second. The Young's modulus is 50 times 10 to the 9, and its density is. Now, with the FVV group, I don't go into Young's modulus that much, but the speed of sound through a solid surface is equal to the square root of Young's modulus divided by the density. Now, the Young's modulus in this case for that marble is been given as 50 times 10 to the 9 over the density of 2.7 times 10 to the 3. That gives you the speed through the marble. Okay, that gives you the speed through the marble, which is 4,303,3 meters per second. Please note that sound through air is 343, while sound in water is 1,500 approximately, and while sound in marble is 4,000. Okay, I assume it's much faster in metals. It's 2.7, not 27. That's 2.7. Okay. So now we have found the speed of sound through marble. meters per second, it's 4,300. But if you want it in kilometers per second, we just divide by 1,000, so it'll be 4.3 kilometers per second. 4.303 kilometers per second. Okay? And that is the answer there, 4.3. Now that's question 5. Now question 6. The speaker, question 6, yes. I'm doing to question 7 today. A speaker is producing 30 watts of sound, so an intensity with a power. The sound wave has a power of 30 watts. At which of the following frequencies would it sound the loudest? Okay. The loudness of sound we know is not just the physical power, okay, but also how sensitive the human ear is. So, because there is a threshold of hearing and where you can't hear anymore. Now, the human ear is most sensitive to frequencies in the mid-range. Okay, so this is between 2000 and 5000 hertz. These are so between 2000 and 5000 hertz. So that would make the only one 1000 hertz is the closest to the peak sensitivity of hearing. Okay, this is in a table in your book in So and Jewett. Now here the last question. So the answer is, let me just write there, equal to 1000 hertz. Reason human hearing is most sensitive between 2000 and 5000 hertz, and that's when it's most sensitive. So the frequency closest to that will give you the loudest sound. Or you can just check in your book. 7. A spherical wave has that form. Okay. The frequency of the wave in hertz is, so we have this spherical wave. What is its frequency? Now, frequency, we know that a spherical wave can be written in that form. I just want to check something. 8 pi r. You just multiply all throughout by r. Just making sure about something. Yes, I do have the correct formula. Pi t is, it's meters, seconds, r meters. Okay. So we know that the general formula for a function is x t. I did this yesterday. The amplitude sine kx minus wt plus minus, or rather wt. In this case, it's a minus, so we'll just stick with the minus angular frequency t. They want the frequency. Now we know from angular frequency that angular frequency is equal to 2 pi times the linear frequency. Okay, but we have been given angular frequency. It is the value just before t. Okay, it's the value attached to the time. Okay, so if we substitute this, rewrite this, the frequency is equal to the angular frequency divided by 2 pi. Okay, so that's the angular frequency. Now we know here the angular frequency is the value just before t. So in this case it is 2720 pi, don't forget the pi, divided by 2 pi. That cancels. 2720, so 2720, 720, there's 360, there's 1360. So 1360 is hertz, is the frequency. 1360 is the actual frequency of this wave. Okay, you just need to know what is the general form of the wave. Okay, that is all that we're going to do today. Thank you very much for listening, and all the best. Have a great